So in this video cast, we'll be in section 16.8, where we'll be talking about the relationship between Ka, the constant for acids, and Kb, the constant for bases. And to illustrate this Ka and Kb relationship, let's look at strong acids, weak acids, and non-acids, and their relative numerical value of Ka. So strong acids, when they dissociate, would give us a neutral conjugate base. The Ka of a strong acid would be really big. It would be on the order of like 10 to the 5th or so. And of course, if you have a conjugate base that's neutral, like for example, if HCl dissociated and gave you H plus and Cl minus, this conjugate base would have a negligible basicity, and it would have a Kb that would be super duper small. Its Kb would be like 1 times 10 to the negative 20th or something like that, maybe even smaller than that. It would not want to get hydrogens at all. Weak acids, on the other hand, would make a stronger conjugate base. And so if we had a weak acid like HF, the Ka for HF is approximately something times 10 to the negative 5th or so, meaning that it doesn't break up a lot. It breaks up a little bit, but not a lot. But this F minus right here could act as a base, and so its Kb would be on the order of like 1 times 10 to the negative 10th or so, making it be decent, somewhat of a base, but not a lot, not a lot. And so depending on how weak the acid, the conjugate base might be a little bit stronger. If it's not an acid, then its conjugate base would actually be a super strong base. So for example, CH4 is not an acid or not a base, but if it was CH3 and it was missing a hydrogen right here, this would be like the strongest possible basic thing, because it would have a super affinity to want to get hydrogens, and its Kb would be off the charts. Here it would be like 10 to the 5th or so. And so you can see this opposite relationship between strength. If something's a strong acid, it's a super weak base. If something's not an acid, it's a super strong base, and conversely, back and forth. This inverse relationship between Ka and Kb, because remember Ka and Kb gives us the strength value of these, is true in all dilute aqueous solutions. And there's actually a mathematical equation that gives this. Ka times Kb is equal to 1 times 10 to the negative 14th, or Kw. So we can make this a handy equation and get rid of the times 10 to the negative 14th and take the negative log of the Ka times Kb equals Kw equation, and then this becomes negative log of Ka plus negative log of Kb is equal to negative log of Kw. And we rename each of these. If you remember from earlier in the chapter, we named the negative log of the H plus ion concentration the pH, and we renamed the negative log of the Ka pKa, and we renamed the negative log of the Kb pKb, and we renamed the negative log of Kw pKw. So now we have another p scale to work with, pKa and pKb. This allows us to say that pKa plus pKb is equal to 14, just like pH plus pOH is equal to 14. Many references, not our textbook, but many references that chemists use, only list the pKa for a particular substance, and then they assume that once you know the pKa, you could find the pKb, you could find the Ka or the Kb, and you'd figure out the rest. So it's really common to just be given, or for the p scales to be used for Ka and Kb, and then they don't have to write times 10 to the negative number for those as well. So here's an example problem using the relationship between Ka and Kb. Calculate the pH of NaF if it equals 0.1 molar and we're given the Ka of HF to be 6.8 times 10 to the negative fourth. I looked up this HF Ka on our equilibrium constants in the appendix right here. So NaF is soluble in water because it's got a sodium in it, and if you remember back from chapter 4, we had a bunch of solubility rules here, and anything in this group 1 area is always soluble, and it's handy to just remember that anything that's got this Na, this K+, those are the two most popular ones right here, always dissolve, and they always dissociate. And then when they dissociate, you get this Na+, that is a neutral substance because it came from a strong base, and this F- right here, which came from, if you add a hydrogen, a weak acid, therefore it could act basic. And so F- could dissolve, once dissolved in water, get some hydrogens and form HF plus OH- right here. And so let's make an ice table for this equation. If we make an ice table for this equation, we know the concentration of this F- right here, because whatever NaF was, that's what F- is, because this is a strong soluble electrolyte, and so this would be 0.1 molar right here. And there would be none of this, and none of this to start with. And then we could use the lose x, gain x that we've used before. And then we end up with 0.1 minus x, x, and x on this table. And if we wanted to know the pH, the thing we'd want to know right here is the OH-, because if we found the OH-, then we'd be into the pH square, and we could find the pH right here. So let's write an equation in terms of the K, and the K would be x squared divided by 0.1, because we're going to ignore this x, and this would be equal to the K of F-, and F- in this case is acting as a base, so this would be equal to the Kb. And we don't know the Kb of HF, and I don't think it's even on the Kb listing sheet right here. Oh. So if you don't know the Kb, what can help you is an equation we learned right here. Ka times Kb is equal to 1 times 10 to the negative 14th. We're given the Ka for its conjugate acid HF right here, and so we know that this times the Kb for F- would be equal to 1 times 10 to the negative 14th. Since we know those two multiplied together give us that, we can write Ka times Kb is equal to 1 times 10 to the negative 14th and solve for Kb. I did the math for you. Kb ends up being 1.5 times 10 to the negative 11th. I can take this number and plunk it right in here for Kb. And then I can solve for x squared, multiply both sides by 0.1, and then square root it. And this number multiplied by 0.1 square rooted ends up being 1.22 times 10 to the negative 6th. And then the POH right here would be the negative logarithm of this number. And then, of course, we could find the pH simply by subtracting from 14. And then you'd know your pH of your solution that had a weak base in it that you didn't know the Kb of, but calculated it because you knew this relationship between Ka and Kb. More on how to decide whether these are acidic, basic, or neutral in the next video cast. So in this particular video cast, you should have learned the relationship between Ka and Kb. You should have learned the relationship between pKa and pKb and a new P scale. And then you should have learned how to use Ka to find a Kb of a conjugate base of a weak acid.